to actually support policymakers both in Europe as well as in China and in India, help them use analytical tools and systems models to design better policies on air quality management. And at the same time, I'm also leading here the so-called capacity development and academic training unit at IIASA, which trains people in systems analysis, systems thinking, and so on. So what I would like to do today is talk briefly about future literacy, what this is and why this is important, and then talk a lot about systems thinking, talk about what a system is, how one can change the system. If there's time at the end, I will also explain the differences between terms like systems theory and systems dynamics and systems analysis. But really the overall objective is to familiarize you with, yes, terminology related to systems, but also improve your understanding of the importance of understanding systems in order to understand behavior of the system, in order to help planning processes, in order to understand designing the future in a more positive way. And I hope some of it is going to be quite interactive. Let's see how far we are getting there. I think the worst that can happen is that I sort of just talk from the lectern and you just listen there. So I'd like you to engage. So future literacy. Future literacy is important to address some of the main challenges that we are facing. And let me just sort of briefly change gear and ask, so what are the main challenges for today? I mean today and into the future. Let me see whether this works. Do you still see my screen and my drawing board? I guess you do. So what from your perspective, what are the main challenges that our societies are facing, particular maybe the African continent? Can I get some input? Is it food system? Is it climate change?
Disasters impacting social services?
Disasters, okay.
Poverty.
Okay, poverty.
Resource allocation.
Yes.
Water and air pollution.
Water and air pollution.
Systems thinking can actually be applied in developing a policy in the public sector.
Developing policy, or what did you say?
Yes, in the development stage of a policy, systems thinking should be applied. It gives better outcomes because you're able to identify all the parties, all those that will be affected and impacted by the policy, and how they are impacted. So for me, it's a good it's a good technique while formulating.
Yes, we'll come to that. We'll come to that. At this stage, I sort of like to get some input on what the challenges are. And then, of course, we will see that systems thinking is the ultimate solution.
Poor governance.
Poor governance, okay.
Conflicts.
Yes, conflicts.
Unemployment.
Unemployment. Okay. Anything else you want to mention at this point? Okay, I mean, that's... Sorry?
Food security.
Food security, yes, very good.
Biodiversity loss.
Yes. Biodiversity loss. Okay, good. Obviously, yeah, these are big questions, and we will not solve all of them. But I think what we already see is that there's a wide variety of topics. Some of them have to do with environmental change. Others have to do clearly with social sector. Yes, Michael or Michelle? Somebody still has their mic on. Okay, good. So the purpose of this little exercise was now sort of to warm us all up to, to agree, or to sort of take stock of what our main, or what big challenges are. Let me just see, where am I? Stop sharing. No, that's fine. I think you should see now that blank, right? So what are you going to do about these challenges? And I think, broadly speaking, there is sort of a standard approach to each of these problems, right? One sort of looks at this problem and then sort of starts to divide this into, potentially into sectors. So if we take, for example, the this issue of biodiversity loss, you start to think about, okay, so what affects biodiversity loss, and is it mostly particular sectors of the economy that are important here, and so on and so forth. And then you form departments in the government, maybe a ministry for this and that, Ministry of Environment or Ministry of Natural Resources, and you try to pigeonhole everything into these sectors. And then you start to prioritize, and this may be based on various criteria that you may want to apply, cost effectiveness or whatever it's called. And then you find the best solution. And I'm actually in the business of doing this sort of standard approach. However, it sort of, it falls short of, I mean, it has a number of shortcomings, and we should really discuss them now, right? I mean, it's not very imaginative. It focuses on individual or single objectives. So all the topics that you've mentioned are all very important, but you will have already appreciated that some of them, if not all of them, are somehow interconnected. And if we're just focusing on one of them, we may be missing the point, and we may be missing what we call synergies, or the trade-offs between solutions of different problems. We also, in this standard approach, we're kind of missing the point of the stakeholders involved. We're kind of just sort of thinking from a single perspective, and that single perspective is a single, maybe social planner or somebody who has sort of the big overview, and we're kind of losing the different perspectives. And the other thing that we're missing in this approach is that there's a whole range of possible futures out there, things one could imagine could happen, which we don't see because we're typically stuck in our mental models on how we see how the world actually works and how things influence each other. And so what futures literacy actually, or let's go back before we go to futures literacy, but typically what happens, I found this beautiful quotation just recently, typically what happens is that decision makers, policymakers, politicians, I mean, a number of people in the public often legitimize certain decisions by referring to, there's no alternative, instead of speculating or hypothesizing about what could actually be. What are the possibilities out there? And that's really important to think broader about what a possible future is. We often open our newspapers and think, oh, these are doomsday scenarios. This is the way the world works. But what we often neglect is that there's a whole variety of things in which way one can affect and influence the future. So I'd like you to be vigilant, and next time you open the news, ask yourself, is the person who's now saying something, or is the news article about something where it seems to suggest that there's just no alternative to the course of action taken, and we sort of with hindsight justify a certain course of action because we think there is no alternative. So futures literacy. Futures literacy is working against that to narrow down the option. Futures literacy is trying to open up the options. It's training. So futures literacy is a skill or the ability to use imagination of possible futures in order to act responsibly in the here and now. So this is not just about science fiction and consuming sort of stories about the future, but futures literacy is the idea is that you use this insight to act now and here. And this is a skill that needs to be developed, obviously. We need to train people, preferably at early stages in their lives, to train their imagination. And that's something that is really kind of interesting or sort of surprising, maybe. If you think about how, who talks about the future, these are all professional, either politicians or they're engineers or there are, definitely experts. But we don't necessarily think about, writers or poets or people who, by definition, work with their imagination on this. So this is kind of surprising, or this is something to remind us of, or we should, be very careful that these kind of aspects are important in education as well. It's not just the maths, it's not just the engineering skills that are important, but it's the imagination that is important. So we should focus on positive thinking and in particular anticipatory thinking so that we avoid the TINA situations. There is no alternative. If we're digging ourselves into a hole, then there may indeed be no alternatives. But the truth is there are always alternatives, and we can anticipate challenges if we are future-oriented. Another way of saying this is this concept, which comes out of the systems thinking literature. It's what is called the iceberg of systems thinking. Many people go around the world, they experience the world as a series of events. They open the newspaper, they watch television, they see the news, and they just see, oh, suddenly this has happened, and suddenly this has happened. There has been a disaster, or there's a piece of news that says people are, unemployment has gone up, or they see a piece of news that says there's a new conflict, or, so and so many people are living in poverty. But what is behind these events, of course, is a series of patterns and trends. And when you start to observe the events, you can make out patterns. And with these patterns, you are able then to anticipate what may be happening in the future. And when you then go deeper and analyze the patterns, you may see underlying structures. And when you then go even deeper than that, you start to identify what are our basic mental models, what are our basic assumptions about the world that make us think and see certain structures, see certain patterns in the events. And it's this, the deeper you go, the more insightful is your understanding of how the world really works and how you perceive it. Okay, we're going to become a little bit more practical, but I just want to mention one method of thinking about the future in the way that futures literacy would like you to think about the future. And that's the method of using scenarios. Scenarios can be used to explore possible futures, to particularly identify desirable futures and not just the doomsday futures. And scenarios, so scenarios in contrast to forecasts or predictions are not there to tell you what will be the case, but rather scenarios are a tool amongst groups of people to start a discussion about the future, how they would like to see the future, what are the constraints, and so on and so forth. So scenarios make the future imaginable, tangible. You can think of different types of scenarios, positive ones, more negative ones, normative ones, where you think about this should be the case, what are the conditions under which certain things are happening or not. And then there are explorative scenarios. Scenarios are a little bit like time travel. You boost yourself into the future and ask yourself, what could a possible future look like? Now, this is a very useful technique to think about the future, but it turns out that it's rather conservative, because we have to base on our scenarios on everything that we know. We just don't have the brains to think about things that we don't know about, right? The famous unknown unknowns. It's very hard to do that, right? And so what we need to do more is to train our imagination in order to generate more interesting scenarios, not only more interesting scenarios, but maybe more relevant scenarios. Okay, so there is a question about in the chat about systemic risk, and I've also seen now that people have identified additional topics. Martha, I don't have off the top of my head a definition of systemic risk, but we'll come to the issue of systems, of course, and possibly systemic risk at a later stage. So bear with me for the time being. Okay, so now, so this is about futures literacy. Again, ability to use imagination to act responsibly in the here and now. One way to, and we said scenarios is a way to do that. Scenarios of what? Well, then we have to think about what do we want to generate scenarios of? And the answer, as you can imagine from the title, is systems. We want to sort of generate scenarios of systems because we understand that the world is interconnected. The world is a big system with subsystems. So we need to now develop a little bit of the sort of terminology and sort of the toolbox for thinking about systems and thinking about systems into the future. So here is a collection of challenges, some of which you have highlighted: waste, for example, climate change, an associated drought, hunger. Sorry, you can think about food security. There's disasters and biodiversity loss, or some of the topics that you had already mentioned. Many of them are, of course, nowadays related or formulated or, if you like, encoded in the SDGs. So the SDGs trying to address these problems. And these people who are protesting here, they have a very important point here. So they're asking for system change, not climate change. But then the question is, what is the system, and what is it, and how are we actually going to change it? And of course, systems thinking has become more and more popular in recent years. Here's some recent publications that use systems thinking in analyzing not only the SDGs, but also broader topics. So, okay, let's then come to the heart of the presentation, so to speak. What is a system? And here is a couple of definitions. of how you can think about a system. I think we all have an intuitive understanding of what a system is. It's a set of connected things that form a complex whole. More specifically, we can say that a system is composed of different parts or elements, and these are interconnected through relations, internal relations between these elements, and they achieve something. So what we need for a system, to be a system, we need elements, we need connections, and we need a function. And you will see what I mean by function in a moment, of course. And the system is organized in such a way that it produces a particular characteristic behavior which is related to its function. So, for example, we may ask, let's now do a little quiz. Is this a system? What we see here on the left-hand side, this is a mechanical clock. Is this a system according to the definition that I've just given you? Any volunteers? Yes or no?
Yes.
Yes. This is a system. What are the parts? What are the elements?
The wheels?
Yes, the internal wheels. What are the interconnections, or how do they interconnect?
The gears?
Yes, the gears. And what is its function?
To tell you the time.
Exactly. Not only to tell you the time, to tell you the correct time.
Time.
Very good. So now we have a digestive system. That's obviously a system that already contains the word system. What are the elements here?
You have the mouth.
The intestines.
Yeah, the different organs, I guess. Yeah.
The stomach, the small intestine, the large intestine.
Right, right. So we have organs, we have, parts of the body that interact, yes. How do they interact?
Circular system?
Well, I hope it's not a circular system. That would be nasty.
To the brain.
But definitely they're interacting in a sense that
this system.
Yes, Eunice? Okay.
Yeah.
So there are different parts,
I don't know if
and they interact because the different sort of the food is going through them sequentially, but then you also have organs that control the whole intestine system, like the liver. I mean, liver and hormones are part of that system too. And what is the function?
Digest food.
Yes. What is another word for digesting?
Break down the food.
Yes, it's all going in the right direction. So obviously the food is broken down into components, and these components are then used as energy, for example, for the body. So that's the primary goal, is to convert food into energy.
Yeah.
There's something I should like to point out. I'm sure most of us will also see it, but maybe for confirmation. Now we have this digestive system in a body, but without the input from the external source, this system.
Eunice, I'm sorry, but I think you're breaking off. I can't really hear you. I don't know whether it's just me. I can't understand your question.
Yeah, I'm not hearing her well.
Yes. So maybe you want to put your question into the chat, Eunice, because we can't really get full sentences on audio. Thank you.
It's okay. Thanks.
Okay, so what about a tree? Is a tree a system?
If we think about all system, forest ecosystem, but there is only one tree, it's maybe it's a system.
No,
Yes,
the tree is a system.
Yeah, what are the elements?
We have the leaves,
the roots,
the roots,
Mhm.
the
Body.
trunk.
Yes.
stem,
Yeah.
The
And how-
fruits
Yes, and the fruits as well, potentially.
for those that have fruits.
Yes, definitely the seeds.
We probably have the soil
Yeah.
on which the
And
fruit
And
grows.
they,
and of course, the soil where without which it cannot even stand and consume.
Yeah.
Yes, yes, there's the soil as well. It could be also part of the system, depending on where you draw the boundaries. Yes. So how do they interact?
So that's also kind of dependent on what we see the trees function. Is its function just to live? Because then all those organs will be supplying it with energy and mass to grow. Or is that tree a consumable product? Then, yeah, our phrasing would be a bit different, right?
Yes. I think this is a super interesting contribution that you're making. First of all, it depends on, in some ways, it depends on the purpose, but maybe the purpose is sort of just coming out of the tree. But I think what you're also trying to get at is that we as humans, we can take different perspectives on this. We can see this as the tree just as a tree standing in the forest, or we can already think about what function does the tree have from an anthropogenic, from a human perspective in our social system. What kind of functions can it have for us? For example, what kind of ecosystem services can the tree deliver? This is already fascinating. Good. So
You can also see it as a source of something for human social system. Charcoal, I can see a lot of charcoal there.
Absolutely, you can see a lot of charcoal. It depends on the perspective that you are taking, especially in systems that have a socioeconomic dimension as well. Okay, what about a pile of sand? Is a pile of sand a system?
That's a tricky one.
No.
no,
Okay, I hear two no's and a tricky.
No.
Okay, so there,
It's a component in a system.
yeah.
so many of you think it's not a system, and I would agree.
It's a component in a system.
Well, if you can also say the pile of sand is a system because it has three main phases. You have the solids, you have water, and you also have air.
I'm not sure I understand the water and the air, but I think you all have an intuition that in principle a pile of sand is just a pile, which means that there is very little structure or no structure at all. It's tiny parts. Yes, you have lots of elements, but it's not clear how they interact. But what about this? Now, suppose the pile of sand actually now is supporting something else. For example, the pile of sand is preventing a rock from falling, right? Now, whether this is intentional or not, but it can fulfill a function, and it can only fulfill that function if the individual grains are coming together or are together and they sort of support each other. And only then the pile of sand can actually support, let's say, a rock from, or prevent a rock from falling. But that's kind of a very sort of idiosyncratic interpretation. For all practical purposes, a pile of sand is probably a good example of not being a system. But one can debate that. But I don't want to go too much into the debate. I just wanted to give you a few more examples. So here is a forest. Somebody said earlier already that a forest as an ecosystem, of course, is a system and has interesting functions, probably not just one of them. And then we can ask ourselves even, for example, this system here that's supposed to be the healthcare system is obviously also a system comprising different elements. They interact with each other and they have a function, obviously, as well. So when we're looking at systems, when we're looking at phenomena, we're asking what are the parts? Do they affect each other and in which way? Is there an overall effect of the parts that are acting together or not? And then there's the question of how does this change over time? So these are the questions that we are asking for systems. Another interesting system is the science system. Science is obviously a system as well. We have interacting parts, we have individual scientists, we have institutions, we have labs, we have students, we have publications, and so on and so forth. All of that together makes up a system.
It's in the dustbin.
Eunice, could you switch off your microphone, please? Thanks. Okay, so let's do a little exercise. Just, maybe you just give me an example of a system, and then we discuss briefly what are the elements, interconnections, and functions of that system. Any volunteers?
An educational institution.
Sorry, I didn't.
School.
What was that?
She said educational institution.
Education.
School.
Yes, education. Okay, so education is a good example. Okay, what are the elements of the educational system?
Students, teachers, policy, the buildings, infrastructure.
The regulators.
Absolutely. Textbooks, a lot of things are falling under the educational system. Very good.
Infrastructure for the school.
Yes. And they obviously interact. I mean, we don't need to go into much detail to describe how they interact. That you need, teachers and students, they interact and they may use tools like school books or computers or anecdotes or just anecdotes or text to teach. And what is the function of the educational system?
Teaching and learning.
Yes, well, there's different functions. Yes, it's to share knowledge,
provide.
maybe. Yes.
To provide skilled human resource, better train to provide services currently and then into the future.
Yes, no, very good. So there's this aspect of there can be knowledge, there can be skills. So critical thinking, of course, is another good skill to have. But there are many, many other skills that education can, of course, provide. Okay, there's another example. Somebody said transportation in the chat. Okay, it's transportation. Let's say, think of transportation as a system. What are the elements?
You have the road infrastructure, you have the vehicles, you have the staff, like the drivers, the conductors, you have the parks or the stations, you have the passengers. Yeah.
Absolutely. And then maybe you have companies that do logistics. You have demand side that needs. You have buses, and you have timetables. All of that. Yes. Interconnections are also very clear, and the functions. What are the functions of the transportation system? Probably also very clear. Moving
to
goods.
facilitate movement of goods and services and humans.
Yes.
I mean, to provide logistics.
Thank you very much.
service provision business.
Yeah, that's also a function, yes. Provide business opportunities for maybe. Okay, yeah, we've already looked at healthcare systems briefly. Settlements can be systems, yes. Urban, cities are systems. That's very good. And then Chris suggested government. Yes, government is also a system, and we can identify lots of elements, interconnections, and of course also functions. Now, for each of these systems, we can also
If I can go, oh, sorry. I wanted to say, I can take the digestive system and zoom out to identify other systems that impact the digestive system.
Yeah, so the digestive system is just one of the systems within the human body. You think about it. So you have other systems in the body.
Other system that can impact it is the nervous system.
For example, you have a nervous system or you have a motoric system, and so on. And we can, I think the point here is that for each of these systems, we can take a step back and think about that system being either embedded in other systems or at least having a connection with other systems, right? So for example, the digestive system wouldn't work without muscles, right? So you need a motoric system also to support the digestion. It wouldn't work without the nervous system because you need interconnections, signals need to be transmitted. And you couldn't do it without the hormonal system. Otherwise, you wouldn't find out that you're that you're full, that you don't need more food, and that you want to stop. And that wouldn't be possible without the hormonal system. So you have a lot of interconnections between the different systems. And in some ways, then systems have that difficult property that it's often difficult to define boundaries. We'll come back to that in a moment. But the point is that systems themselves, because we know that individual items cannot be separated, so systems cannot necessarily be isolated. Okay, you've probably all seen this picture, and that's sort of, it's supposed to show, supposed to be a metaphor for what a system is. The elephant and the six blind men. Each of these six blind men, they touch a part, and they tend to think that what they experience is the system, and they're convinced that what they are seeing is the totality of the system, or they understand. But obviously they only see one aspect, or they rather sort of imagine just one aspect of the more complex reality. Now, what I want you to notice is, this is, it's a no-brainer, but for people who see this for the first time, it's kind of enlightening to see that you can look at a system from different perspectives, and you can come to completely different conclusions. The point here is that each of these blind men, they see the reality in terms of what they are already doing relatively well. So the guy who sees the tree, he's probably an expert on trees, and he sort of feels the trunk and says, yeah, that's my expertise, this is what I know, right? And they probably say, I could do a little bit better if I had better resources. If my part in this analysis would be just better, or more important. But the truth is, it's not about singling out one of them, but they all together, if they talk to each other, they may come out with a completely different conclusion. So what this picture is showing, that these people completely, at this stage, they completely ignore the others, right? They just think about what they feel. They don't talk about it yet. But they tend to completely ignore what others are doing and what others are thinking. And that's, of course, a big mistake. And what is also important to see is because they're blind, they cannot see the whole, they can only touch parts of the elephant. That's sort of suggesting that each of them is very limited in what they can do. They cannot see the big picture. They can only feel a local part. And that's often the case when we human beings are talking about systems. We can quite well understand parts of the system, but we often cannot really understand the whole. And this is where systems thinking can help us a little bit. Obviously, some complex problems are just very complex, but at least systems thinking is a way to open up to other people's perspective. Here's another picture which I really like, which is sort of showing what systems thinking can be about. And that's the broken mirror. In this broken mirror image, the idea is that we're studying nature or we're studying complex problems by breaking them down, by breaking them into smaller bits. And when we look at individual parts of this broken mirror, we get a pretty good picture of a very specific aspect and a very specific part of that overall big system. So locally, it's a pretty good picture and can be pretty accurate. The mirrors can get better and better and better. But because the mirror is broken, we never see the totality of the system. And again, that's where systems thinking can help us. But it's often so complex that we need to work together. Okay, so the conclusions from this part is, I hope I've driven this part now home, is that systems have parts, interactions, and functions, and they function really holistically. So we cannot break them down into smaller bits to get a concrete to get the full picture. Not just that, we can analyze them, but we need to put these things together again. And that's kind of often difficult. Okay, short pause. Any questions so far on what was said?
Yeah, Fabian, I have a question.
Yes, please.
Let me turn on the camera as well. It's nice to see you again. So all of the systems they are placed upon a context or placed within a context, right?
Yes.
A system is a part of a bigger system, and then is there an imagination where this would do we have an imagination if this would end at some point, or are we just observing systems within systems within systems, and that would never allow us to see the bigger picture, right?
Yeah, I think it depends on the context. I think the system of systems is really it's kind of the system. The biggest system is kind of the world as a whole, right? And then you have to somehow always define in which context do you want to look at it. Often what we do is we need to narrow it down, and what we often do is we narrow it down so far that we're just looking at this piece of the mirror again, right? And so we have to find a way between figuring out, we have to figure out a way to look at phenomena and issues and problems in such a way that it's not becoming trivial in the sense that we're saying, but the universe is big and it's so complex that we cannot do anything about it. And this on one hand, and on the other hand, that we break it down so small into such a narrow bit that we kind of completely lose the context, right? So I think what you're referring to is that yes, in principle, we're running the risk of what is called amongst philosophers the infinite regress, that we always keep asking why and why and why and why, and there's a sort of a first mover maybe at the end of that line, and then we may get lost. So yeah, we have to be pragmatic, and that's why we are at this institute a little bit proud to say that we're doing applied systems analysis and not just systems theory.
Also a comment to make myself.
Yes, please.
It looks like in this system, I think the part itself, just like when you look at the body, each part, no matter how small it is, it has actually a role and the function it is.
Yes, yes.
It's something it is giving to the system.
Yes.
And I think that's the tragedy of our management of the environment, because we don't see the role of a particular part, and therefore you say, let me take this particular piece of land, do this type of agriculture, then you don't realize what you have actually done to that part of the system by just taking a piece of land and doing some agriculture or building a building on it.
Yes, this is exactly, if you like, you've already achieved the learning objective for this exactly, that in principle, so two things. First of all, one can make the trivial statement and say everything is connected to everything, right? Now, if you take that stance, then you're running the danger that you're just completely helpless, because then everything can influence everything, and everything is in flux, and it's really, really complicated. So it's about aggregating what's going on, or sort of identifying what are handleable units. I think this relates also to Tara's question. So think about what are handleable units, but what these handleable units are, that's a matter of a perspective. And maybe a industrial farmer, they may take a particular perspective on the land, and maybe the smallholder farmer may have a completely different perspective. And one cannot say one is right and one is wrong, but one has to talk to each other and understand each perspective to get at least a more comprehensive assessment of what is going on. And of course, what you're saying is right. There's lots of unintended consequences involved in systems, and we're going to see some of them in a moment. Okay, I would like to. Yes, please.
Systems thinking. Can you situate it with in our current situation? What obtains currently, where there's a lot of emphasis on specialization. In my opinion, my experience, specialization actually tends to be at loggerheads with systems thinking. Have you seen this in this way, or am I wrong?
I think there is, thank you for that question. That's, again, super interesting. I have a really cool audience today. I think there's various ways to think about it. So first of all, per se, specialization is not a bad thing, because you need to understand the details often in order to be able to then think bigger again and aggregate and integrate up and so on and so forth. So I'm not saying, if I say systems thinking is important, I'm not saying that we don't need specialists, but what we need, so think about the elephant and the six blind men. These are all specialists, and it's good that they are specialists, because they are the specialists who can explain exactly what they feel, and they can make differentiations that maybe a layperson may not be able to do. But what we need in addition to this specialization is, again, some integration, some synthesis, not just the analysis, but the synthesis. And for that, you need specially trained people who are, on the one hand, who are, let's say, familiar with systems, with systems thinking and systems methodologies. But you also need a particular kind of people who are willing to cross boundaries, right? Who are not afraid to talk to people from a different field, with a different expert, with a stakeholder who is not an academic. So people who are willing to use what they've learned and their academic knowledge, if you like, or their knowledge, and they're willing to use this for a bigger purpose and cross boundaries. So at an individual level, you need people who are confident enough to step out and say, hey, I was trained as a biologist, but I'm happy nowadays to talk to economists and to physicists and to civil engineers and to policymakers to find a solution. So that has to work at the individual level. And then one can take a step further up and ask ourselves, what are the institutions that make that possible? And so again, you need to have an institutional infrastructure that encourages people for doing that. Not everybody, but some of them. So you have what is called boundary organizations, like IIASA, the one that I'm working for, where this is happening very naturally. You have other boundary organizations that integrate people from different fields. Some universities are trying to do that in the sense that they are trying to set up interdisciplinary studies or broader studies. And I'm not blaming the academic system that not everybody is doing that. As I said, we need specialists, but we also need to have that cross-cutting ability at various levels. Edward.
Yeah. Hi, Fabian. Yeah, thanks for the time and thanks for all the explanations that you've given so far. Just a quick comment I want to pass here. So basically, I'll give myself as an example. I read chemistry for my first degree. I went on to do nuclear and radiochemistry for my master's.
Yeah.
And then I went on to do isotope hydrology and hydrochemistry at the School of Environment and Sustainability. And so basically that's an interdisciplinary school where I have the opportunity to interact with people in various work in various aspects of water. Now I am a professor at UMCSP, where we have a school of collective intelligence, where again you have people from broad range of backgrounds coming together to look at problems and challenges from various angles. These are specialists, as we mentioned, and trying to distill what solutions will best work for every problem that you may have. So for instance, we're talking about this water, energy, food, nasal studies. So you bring water experts, you bring energy experts, and we kind of like trying to interact here and there to see how, if you solve the water problem, how that will go along solving an energy problem, solving agricultural problem, at the same time solving a health problem. And I think that's one of the things also that kind of like attracted us to this particular call. So if I just a little bit philosophical question though, like we are encouraging holism, if I may say, rather than reductionist approach to problem solving. But in your experience, if we throw out a call like this without this kind of seminars that you are organizing, do you think that we can actually work to come out with things that will meet the expectations of experts like yourself, probably who will be reviewing this course? And if you also don't have institutions that encourages this, or people who have been in such systems for a long time, but they are applying to this kind of course, I'm wondering how, again, that expectation will be met. The approach and how all these things kind of like distill together to get what the objective of the call is supposed to kind of like achieve. Just something for your comment.
Yeah. So my understanding is that question is related a lot to the Belmont context.
Exactly.
And I cannot really speak to that because I'm not involved in how the calls are designed. My understanding is that there are ideas to sort of to prepare you with a training like this, to sort of a general thinking about how things are connected. I cannot give you advice on individual proposals under this call. But I think the purpose is to open up your minds again to think about, yes, okay, so how do we address the water security issue in the context of food security issue, in the context of climate change, in the context of energy, and that this is totally fine to make these connections, but be also clear that you cannot solve all of these problems at the same time, but that you need to focus. But the systems perspective, and we'll come to that in a moment as well. One of the aspects of systems analysis or systems approach is that this is all about, often all about co-creation. That a design is not just designed by, or the questions that we formulate as academics, and that we do our research on, is not just designed by ourselves, right? But since we are tackling societal problems, we need to work with the stakeholders that are involved in these problems, and that is civil society, that is the various government agencies, that is the people who provide, or the organizations and companies that provide certain services, and so on and so forth, right? So we are not doing, and excuse me, this is not, but it sort of fits in nicely now. So this is not nuclear physics that you have to leave to the specialist or isotope chemistry, where the research questions come naturally out of the science itself. But here we are dealing with questions that are of broader interest and need to be addressed by a broader constituency.
Okay. Yeah, thanks. I just want to pick your thought on that. Thank you.
Yeah, sure. Thank you, Edward. Kofi.
Yeah, thanks very much. No, I was just going to put in the idea that, yes, within the system, the parts are more specialized, but within the specialized, they are always found some part of the speciality that links to the other parts.
Exactly.
Yeah.
Yes, they interact.
They interact for the interaction to occur.
Yes.
If they don't find any common grounds where the linkage will occur, then there'll be no more interaction.
Right.
So that's one.
And they're not part of the system, right?
Yeah, not part of the system. Thank you.
Thanks. Olusola?
Yeah, thank you very much. I hope you can hear me. Can you hear me?
Yes, very well.
Yeah, my question is more or less, allow me to say, political one within the discourse. Taking system thinking, for example, based on what you've already discussed, within the disciplinary systems, there are some academic, with some people with certain academic background, they believe that their discipline is more superior to others. So when you have this kind of arrangement where people need to work together on a well-defined problem, and you bring different people with different academic background, different worldviews and experience together, somehow we have this power problem. Some feels they know more than the other, and they want their opinion to actually prevail over some certain group. So in your experience, an experience of institution that personally I've been following for more than 10 years now. So how do you manage this power dynamics within a system in this context when you have an issue to work on and you want to bring economists, social scientists, natural scientists, you need to bring everybody together to work together. And so how do you manage this kind of power dynamics in a situation like this? Thank you.
Yeah, thanks. I think this is also a very, very interesting question. Obviously, there's no panacea to this, but I think the first dimension we need to be all clear about is that, and it helps remind people of this, is that, is a certain, humility is in place. That's what you're saying, right? The challenge is that some people are not humble about their own field because they think it stands in the hierarchy sciences or academic disciplines may be higher than others.
Yeah, exactly.
But then maybe, you know, a pragmatic solution could be to just sort of have a discussion with them and think about, or ask them, so how do they think that their discipline alone will lead to the solution to a particular challenge? And again, I think we are all clear that disciplinary problems can just best be met by the disciplinary specialists. But as soon as we study the problems, I mean, of today, then we kind of realize that it's not possible to put these issues into the pigeonholes of academic disciplines. So I think, yeah, I mean, a constructive way is just to sort of to figure out, okay, listen to them, how far can it actually reach? And then probe them and ask, so what practical advice, let's say, what practical advice would an economist have in the context of water pollution? You know, you need to understand the details and the geographies and the hydrology and so on to understand the details of the problem. It isn't just enough to say, well, we need a taxation system or a whatever economic system. So I'm a little bit vague about that because it depends a little bit on the context, of course. But I think when you actually probe people, they will find it difficult to explain how the problems will actually be solved, right? And I mean by really be solved or addressed, and not just on paper, not just by writing another academic paper, but rather by actually bringing about change, by bringing about action amongst policymakers. And clearly, policymakers are colorful people, probably. Colorful in the sense that they need to listen to many different people. And it's not just academics, obviously, that they're listening to, and not just economic advisors, but they are actually quite familiar often with looking at problems from different perspectives. They look at it from a budgetary perspective, from a populist perspective, if you like, from a maybe substantive power perspectives, and so on and so forth. So policymakers themselves are probably a lot more open to systems thinking than many of the academic specialists. Okay, I want to move on and talk a little bit about how we actually can represent systems. As soon as you start to think about it in a more concrete way, not just abstractly, then you need to think about, how do I actually describe the system? How do I put it on paper? How do I can show a system, or what I mean by a system, to other people? And the problem here is that, yeah, systems happen all at once, as it says here. So you need to have a language to talk about systems, and diagrams are particular useful ways to think about systems. And they tell you already a lot by just looking at diagrams. Now, as the second bullet says, diagrams are models. Again, models of reality, obviously simplifications. And somebody has said in the past, all models are wrong, but some of them are useful. And this is how I'd like you to think about models, that they are all wrong in the sense that, of course, the model isn't the same as the reality, but they help, or they can be helpful or useful to us in describing and understanding and communicating about what we think is the world. So again, think about the elephant and the 6 men. Then the elephant, as we've just seen as a cartoon, is also just a model of a real elephant, of course, but we understand, of course, very well what the image tried to tell us, namely that we need to look beyond the individual disciplines. So the diagrams help us to understand and eventually also to develop strategies for better action. So here's an example of how we can represent a very simple system. We have elements we can delineate by circles, and then we have arrows that show us how the interaction then works. Here's another representation of another system. So maybe you have sort of 3 elements here. You have an information, you have action, and you have a result. The action leads to a result, and the result will then help us to update our information about the problem. And this new information may help us to adjust our action that we initially took for addressing the issue. Now I just have to briefly find my Zoom window here. Okay, so these are very simple representations or diagrams of very simple systems. Another type of diagram are so-called stock and flow diagrams. We think of the world, or in some circumstances, we may want to think about the world consisting of stocks. These are physical entities, can also be non-physical entities, like let's say a water. Here's the example of a bathtub, where the water in the bathtub can be considered a stock. A stock changes relatively slowly in a system. And then you have flows that can change stocks. So in this case, you have water coming in through the inflow and through the faucet, and it's also flowing out. But you can apply this image of stocks and flows, as I said, not just on physical systems, but for example, if you think about knowledge, then of course you can also think of knowledge being a stock, and then education increasing that stock, and people dying out is maybe then considered as an outflow out of the stock. These diagrams are very good in representing sort of feedbacks. So for example, in this case, we may not just have an inflow that influences the amount of stock, but the stock itself may have an influence on the inflow. And as soon as we have this, then we have a feedback loop where the stock influences the inflow, which itself then influences the stock, and it goes on in circles. So going in circles in systems is actually quite common. We call these loops, and we can have what are called balancing loops, and we can have reinforcing loops. We come to that in a moment. Obviously, the same can be true for the outflow. These different diagrams, I'll explain in a moment, can be quite sophisticated and quite detailed, but they can also be very simple to just sort of describe sort of the elements of the system and how they influence each other. Here we see already a more complex diagram. So this is a very simple population growth model. We have, on the one hand, we have a population, which is our stock. We have births. In some ways, these are not stock variables, but these are flow variables, the flows flowing into the population. The plus signs here mean that the population is influencing positively the births. So if the population goes up, the number of births is likely going up, and as the number of births is going up, or as the number of births is going up, the population is increased. Now, this model is a very simplistic model of how food supply may influence the population. So here we have a positive feedback loop. Down here we have a negative feedback loop. Population leads to lower food supply. So this is expressed by this negative sign. The food supply, sort of an increasing food supply, is leading to higher births, an increasing food supply, decreasing food supplies, but also leading to more deaths. And so then you have two factors affecting the population, births and deaths, and then the exact dynamics will depend on what the actual numbers here are. This is just sort of a qualitative analysis of the system, and you can already sort of reason your way through it. Of course, once the system becomes relatively complex, and as this already starts to become complex, you start to simulate this system on a computer with specific parameter values. And then you're already in the business of modeling, which is one way of thinking about systems, but of course it's not the only one, but it is useful to be aware of the basic toolbox that systems analysts have here. We generally we make a distinction between causal loop diagrams and stocks and flow diagrams. The causal loop diagrams, they're super useful when you just want to have sort of a higher level point of view of the system. As I said, I've explained, we have arrows, we have stocks or flows. Sorry, we don't have stocks and flows, we just have sort of phenomena. We have a population, we have births, and by these arrows and the signs, the plus or minus signs, we just allocate the relative influence of one element onto another. We use symbols like this, this bend arrow and the R to describe reinforcement loops, but we can also have loops where which are balancing, which we'll come into in a moment. And then these stocks and flow diagrams, they have a higher level of rigor. They distinguish flows and stocks from each other. You need to understand here a little bit more what the actual units are. So here on the left-hand side, the causal loop diagrams are more qualitative. Here, you really have to make sure that all the units match in order to be able to put this on a computer and simulate this. So here, just alternative representations. The red one is one. This is essentially just the same thing. This is a little bit more rigorous, the blue one, because here we are kind of seeing that the birth rate, sorry, the births is not just a function of the population, but it also depends on the birth rate, which may itself be dependent on other factors. The S is just the same thing as the plus. S stands for same direction. As the population increases, the birth increases in a similar way. And here on the right-hand side, the blue stock and flow diagram, again, is a little bit more explicit. Again, the births are in this image not just a function of the population, but also of the birth rate to make it just more explicit. So I had anticipated a little exercise that we sort of pick a system and then construct a diagram, but I think we may not have enough time for that because we've already spent quite some time on very, very interesting and important questions. So I want to skip this, but this is something that you can do if you like as a homework or consider as a starting point for further thinking. I wrote here in quotation marks the 5 times y rule, which is a useful way to think about how you can construct causal diagrams or a good starting point for understanding a system. The good thing about systems is you can start anywhere in the system. So if you think about, let's say, one of the things that we've discussed earlier was kind of food security. And if you want to now construct a diagram of your food security system or food security problem, you can pick any part of the system and use it as a starting point, and then use the 5 times y rule to ask 5 times the question why. So for example, and then move your way sort of backwards through the system. So for example, you may ask the question, so food security, well, if food security is the theme, then, well, how is food supplied? And then you're asking that question, the why question, so why or where in that case, where does the food actually come from, where is it produced, and why does the food system depend on what does the food system depend on? What are the factors? So you're going up the ladder, if you like, of an infinite Y regress, but you only take 5 steps. It's like you're a small child and you're asking, why is this the case? And then your parents will explain to you, well, this is because of this. And then as soon as you go into this mode, you have a causal relationship. B happens because of A. And then you ask, well, why is A happening? And then you need to find a reason. And so you slowly build up that diagram to understand the system. Here's an example of a food supply system that focuses on urban food. And this is what its sort of typical diagram may look like, a diagram that is feasible for analysis. Of course, if you have too many elements in the system, which you tend to do as a beginner, you start to sort of ask, go through this process a number of times, and then you have like a diagram that becomes really, really complex. At some point, you need to aggregate and simplify and ask the question, what is really important here? What are the really important factors, so that you don't fall into this trap that Taha was referring to, that you could see, of course, or I guess it was Olusola as well, everything is connected with everything, and so you can draw a really, really big diagram, and that's of course not very helpful. What we see here is, again, elements. We see blue arrows with plus or minus signs, and then somebody has done the analysis to figure out, well, if I go through this loop here, is this now balancing or is it reinforcing? So if I have a food availability gap, what does it mean for urban population? If there is not enough food, well, urban population will not grow, it may decrease. But if it decreases, then the demand goes down, and that means that the food ability gap will actually decrease. So what this means is that if you start with a big gap, if you go through the circle once, you will get to a smaller gap, which means that the loop itself is balancing. That's why it's called B, and the numbers are just numbering from 1 to 4, because we have 4 loops in the system. What is a little bit unintuitive, and if we had more time, we would do exercises for this, is that the plus or minus signs are not saying, okay, if I have more food demand, if I have more population, it means that it goes in the same direction. So it means, obviously, if I have more urban population, I have a higher urban food demand, but it also means that if I have a lower urban population, then the urban food demand goes in the same direction. That's why it's the plus sign. So lower urban population means lower food demand, not a plus sign just because, the plus is not saying more food demand, but rather it has the same sign as the population variable itself. Okay, this was sort of a short excursion into system diagrams. They can become complicated, but they form, and that's why they need to be simplified, but they provide a really, really cool tool to talk to other people about how you see the problem. And what we often do is we start an exercise like creating a diagram, a causal loop diagram. We do this, we do these exercises to bring people with different disciplines or with different backgrounds, with different perspectives together, so that together they design such a diagram, right? There's no point in me as a single person to design a diagram of a problem. That may be just my perspective. But if you really want to have a comprehensive view, right? Think of the 6 blind men and the elephant. Then we need to have all kinds of perspective on what the issues are, how they are related, and how they influence each other. Okay? Good. Any questions up to this point? It's literally just a very short introduction into these diagrams. The diagrams will then be used to, as I indicated, to model the different systems in more and more sophisticated ways. Oh, Martha, please.
Just one practical question. Which tools are you using to create these causal loop diagrams?
Yeah, so these causal loop diagrams, they can be created by software, which I think is readily available. I'm not sure whether Stella is doing this. I'm actually not using it. So these causal loop diagrams, these very simple diagrams, can be even done with PowerPoint, on paper. As soon as you start to use the tools to actually model, you need dedicated software. Two softwares come to mind. One is called Vensim. The other one is called Stella. They're all open source. They look a bit outdated, but they're useful tools to analyze systems like this. Thank you for that question.
Thank you.
Okay, then just briefly move on and talk about something about systems that we knew already, right? Systems are connected, and in a sense, we want to disentangle systems from each other. We have, as I said, it's kind of arbitrary to cut a line somewhere and say, this is the end of my system, and then the rest is outside the system, but it has to be done. The message here is it's totally fine to talk about systems and how they interconnect and systems of systems, rather than having to talk about the universe as a whole and nothing else between there and maybe the elementary particles as the constituents. And that's leading me to the next point, and that is typically that we have in systems, we have a hierarchy. So we can think of a system operating at a particular level. We have interacting elements. We have a boundary around the system where we say, well, there's maybe a little bit of energy or mass or information coming in or out of that system. But in principle, we have a closed or almost closed system. But then that particular system can be, or elements of that system can, of course, be systems themselves, which we didn't see or didn't want to see when we were operating at level n. So we simplified it and just said this is a closed system with a particular reaction, but of course it may have inner workings. And similarly, our system can be part of a bigger system which we may want to analyze at a higher level. So an example, and where we draw the line and say, well, this is a level, this is a separate level, the practical conclusion is here. Whenever the interactions between the elements are stronger than the interactions with the outside of the system, or what we consider outside the system, then we can draw a line and say that's kind of a system that we want to study separately. But as soon as the interactions with other parts of other systems become strong, then we need to reconsider our configuration and maybe change our intuition of what we mean by levels. Yes?
Yeah, can I ask this? When you say that these apps are open access, exactly what do you mean? Can I just go to the internet and download and start using?
Yes, exactly. That's what it means, and it's relatively straightforward. I know a little bit. Vensim was developed, I think, in the 1990s. At least that's what the software looks like. Looks really old-fashioned. It's a small executable file, and you have immediately a dashboard where you can get going and design your diagrams. Yeah. So open access doesn't mean just sort of open access for programmers, but it literally means you go to the website, you download it, you have a tool, and you can start using it. Okay, so here's an example of where these sort of hierarchies become very, very clear. We're all familiar with this hierarchy that we can start to think about the world, and this is a relatively reductionist view, that yes, we start with elementary particles or molecules, and then these come together to form cells, and the cells from organisms, individual organisms, and then this becomes already kind of quite interesting. Then we have actually populations of organisms that may have social interactions as well. We have communities, we have ecosystems, and then we have the biosphere, and of course, at the top of it, we have the whole universe. Again, that's sort of a standard way of thinking about these hierarchies, and depending on what kind of questions you're asking, you are operating at a particular level, and that's not better. To come back to the question of certain disciplines consider themselves maybe better, or whatnot. It's just a question of what is appropriate. If you study social interaction, then it doesn't make sense to work at the cell level. At the same time, when you're studying diseases, you can do this at different levels. You can do this at the community level, or at the population level, at the group level, or even at the level of cells. Nowadays, we're actually studying diseases, of course, also at the molecular level. Nothing is wrong. It just means you're operating at different levels, and you need to be aware that there are other levels as well at which you can maybe answer similar questions. Okay, I talked already a little bit about system boundaries. And what we consider within the system and what is part of the environment is in some ways a little bit of a convention. And it depends very much on the context and on the kind of phenomena that you are interested in. Of course, if you have if you think about a physical system like a warm room that you want to insulate against the cold, then that's part of your system, and the cold outside is the environment. But if you look at it from a different angle, you may see that the walls are actually maybe transparent, and therefore the distinction between what is the system and what is the environment is not so clear. This is a relatively static point of view. A more modern view is sort of to take a more dynamic view that for a given system, we have kind of an input environment and an output environment. They may overlap, they may interact, there may be a feedback from the output into the input environment, which is happening in many systems, of course. So system boundaries, one can say probably a whole lecture course on system boundaries and how to define them and so on. Again, this is just a catchphrase or a keyword for you to remember that in systems analysis or systems thinking, it is important to draw that distinction between a system and its environment. And so we come back to our iceberg example. If we think about, again, what is the system, what is the environment? Again, most of what we perceive is happening at the events level. So we don't really understand the systems, but we just sort of see it. We sort of understand, or we observe the output of systems. And in order now to understand patterns better, we need to go a little bit deeper and understand the relationship between structures and behavior, or structures and events. So the way to do this, or systems thinking, the whole systems literature is now full of examples, or has sort of, full of examples of how structure and behavior are related to each other. So typically what we think when we think about behavior of systems, well, we think mostly about behavior of people, and we think behavior maybe largely depends on character, on circumstances and whatnot. For systems, we have a very clear notion that whatever the system does, how it behaves, is only determined by the structure. And if you have a biological system that has a certain structure, and a social system that has a similar structure, that has elements that interact in similar ways as a biological system, then the behavior will also be similar. So here's an example of what I mean by behavior. So for example, exponential growth or exponential decay is a phenomenon or behavior that we know from very different systems, right? So in demography, we're working with exponential growth and exponential decay models to describe the population dynamics. But this is also true, or this can also be applied for resources. It can be applied for biodiversity, money in the bank. It can be used for in hydrological systems and so on and so forth. So this is a behavior that you find for systems across disciplines, which makes it super fascinating to think about, well, how does that behavior actually come about? What can I say from a systems point of view to describe what's going on here? And the answer to that is that for a given behavior, there is always a particular structure, in this case, a very, very simple one, which we already encountered, and that is we have a particular condition, right? So for example, we had a population, right? And then we had a growing action. And the key here now was that the growing action has the same sign as, or the relationship has the same sign in this direction and also in this direction. So we have a reinforcing loop. Okay, I think, yeah, okay. So what this means is that whenever we encounter this kind of structure, that we have a condition and a growing action and two same sign relationships, we will end up either with an exponential growth or with an exponential decay. Right? This is a simple reinforcing loop. There are other structure behavior pairs. So when we see this kind of goal-seeking behavior, we know that the underlying structure roughly looks like this. We have a status, a condition, an actual level. We have a goal, a desired level, right? And the relationship between the desired level and the actual level defines what we mean by the gap that needs to be filled. We then see a corrective action, and this corrective action affects the actual level, right? So if we see that the actual level is, if there is a gap, if the gap is big, then we see a corrective action which goes into the same direction. Bigger gap meaning bigger corrective action. Bigger corrective action meaning there's a big change in the actual level. If there's a big change in the actual level, then the gap is going to be small. That's why we have an O here for opposite direction. And then the desired level, if the desired level is big, but the actual level is low, then the gap is big, and so on and so forth. So what we have here is a already relatively complex behavior. We see this behavior, for example, in control systems, where there's a particular goal given. Think, for example, a thermostat, and then there's a corrective action changing the actual level. Okay. So suppose this is now our understanding of a goal-seeking behavior, or represent this is the structure. If we have a goal-seeking behavior, well, what about if we now introducing a delay? Suppose we are observing a gap, but between observing the gap and taking the corrective action, there's a delay. And then there's also a delay between taking the corrective action and an actual level. So think about it this way. We have, for example, let's say a desired level in a supply chain, where we observe a gap, there's not enough product in a supply chain. We observe that, but before we take action, some delay is happening. And there's also some delay before the actual stock of a product will be supplied. This can be any supply chain. You may want to think about water as an example, or food. Think about a food supply system. What if we have delays? What kind of behavior do we expect then if we have this kind of delay? Any suggestions? Yeah, Taha?
Each of them creates a subsystem around that delay.
What does that mean? A subsystem creating?
Yes, so the delay should trigger other parts of the supply chain also to malfunction or function differently. So
right, yes. So there's some kind of it certainly changes the feedback in some way. Yeah, Mikkel or?
Yeah, I was saying there could be a catastrophic result, like death because of a famine.
Yes, absolutely, right. If there's a delay, then that means that there could be eventually that there's not enough food, of course, and if we think about the food system, right? So the answer to the question is actually that there's going to be some oscillation, because what happens is that so we are trying to close a gap. Let's say there's too little food, but so we want to increase the amount of food, but there's a delay, and so the gap widens and widens and widens. The supply goes down. Before the supply is going up again, the supply is actually going down first until the corrective action actually hits the actual level. Then we are producing more and reducing the gap, but at some point we're producing too much. And so we actually now need to reduce now, but this signal also comes with a delay. So we are producing maybe too much for some time before the corrective action is actually taken. And so we actually see some kind of seesaw behavior. This is another way of actually highlighting this. We, in an economic system, we want to match supply and demand, and we can think about supply being driven by by one part of the system, if you like, the supply system, and then you have a demand system. But if there's delay in the system, then the signals between supply and demand cannot meet each other in time, and so we then have an oscillation. And from physical experience what it feels like to stand on a seesaw and trying to balance with somebody across, if the reaction time of you guys standing on a seesaw is too long, right? If you have an instant reaction, it's relatively easy to get into equilibrium. But if the action is delayed, you will always have this oscillation between going up and down. Okay, here's another structure of a simple system where you make efforts. So here's the example that you're maybe in a company and somebody makes a good effort, makes good performance, gets good feedback, makes more of an effort, and so on and so forth. So you have a reinforcement effect that is essentially an exponential growth. However, if you have a good performance, there's also a limit to how much you can actually do. Let's say the week has only 168 hours and you need some sleep, so you can't do work. So you have a limit to how much your performance can actually grow. So the constraint will actually then lead to the fact that your reinforcement loop will be balanced by a balancing loop to give you an overall performance. And what we observe here is some kind of limiting growth. There's an exponential growth at the beginning, but then there's a leveling off until you hit some kind of maximum performance. And we see these behaviors in a lot of systems, whether these are innovation systems or just river flow systems or whatnot. So there's a lot of structural richness in these very simple examples, and they can explain a lot of the actual behavior in the real world. So we said the system's behavior is now the result of an interplay of positive feedbacks and negative feedback loops. Some of them stabilize, some of them grow, and we have some kind of sort of archetypal, we call it archetypal behaviors that we observe in these relatively simple systems, and these archetypal behaviors we see also in the real world. And the whole point is that there are these what we call archetypes. So these are well-described simple systems, like for example this one, right? This is a really well-defined and understood system with a very well understood dynamics. And we can use these archetypes, these simple structures, to understand more complex systems by reducing the more complex systems in essence to the more simple systems that have the main features of the main systems. And again, this is not necessarily when we think about systems thinking and not very concrete scientific modeling, but rather in the context of systems thinking and stakeholder analysis and stakeholder engagement and so on. These are simple tools that you can use to explain people basically what's going on. You can explain to them that what you have in the systems is a balancing loop that is delayed when you see this kind of behavior, and you can start looking for it. You can start to look for where is the delay in the system that leads to this behavior and does not lead to a stabilization, right? So this is the purpose of these systems archetypes. Okay, so the take-home message from this part: system structure determines the system's behavior, and from the behavior we can draw conclusions about the system structure. Just a few words about resilient systems. So there was an earlier questions about systemic risks, where the characterization of the systemic risk is that it is a risk that affects the whole system. It doesn't affect just individual parts. So, for example, you know, if your house is on fire, then this will affect probably all the members of the household and maybe the neighbors. But in principle, if the fire brigade is doing the job well, then it's not that the whole economic system is endangered or the whole water supply system or something like that. But it's pretty much contained to a small area. When we're looking at systemic risk, we're looking at disturbances to the system where the whole system is affected. This is described in the system, and then we talk about a term which we call resilience of a system, to measure how much is the system disturbed by a shock, how quickly can it absorb the shock, and how quickly can it recover and adapt, and then maybe can it actually outperform its performance before the shock. So that's a useful term. You've heard it a number of times. It's a systemic property. This is not something that is inherent to any of the parts of the system, but it is a property of the interaction of the individual elements in this very specific configuration of a system. And that makes it difficult to measure, because you cannot just look at individual parts to establish the resilience. For example, you cannot look at the operation of an individual hospital or of an ambulance car or of a particular doctor to figure out what is the resilience of your healthcare system. You have to look at it from a systemic point of view, and often the only way that you can figure out how resilient the system is by actually disrupting it, or, you know, obviously you don't want to do this, but you can often just with hindsight tell whether a system is resilient or not. Of course, there are factors that improve resilience of a system, like redundancy and so on and so forth, but to measure concrete resilience is a difficult task that can only be done ex post. Okay, so let's come back to the iceberg analogy of sort of systems thinking. You can start at the events level. You can just take note of what has just happened, but typically what you want to do as a systems thinker, you don't want to just sort of say, so what do I see? What is just happening? But you also want to ask that question, why do I see what I see? This is the relating to the 5 why questions, that you start to think about what what brought this particular effect about? What are the causes of the effects that I'm actually starting to see? So what are the facts, or what are the causes that contribute to the issue? And then you can ask yourself, well, why do things actually stay the same? So we've raised a number of challenges that we are observing, ranging from biodiversity loss or poverty and so on and so forth. And then you can ask yourself, well, why is it that we cannot alleviate poverty? Why is it that we cannot mitigate climate change? Why is it that we cannot halt biodiversity loss effectively? And that already brings you to, in this iceberg image, further down to the patterns, to the underlying structures. What is it? How does the system actually operate? And then finally, you may want to ask, well, why things do change at all? If it was so static that never anything can change, then of course you would be in a poor situation. But of course, things do change. The supply of water changes over time. The amount of food changes over time. Prices change. Why do these change? So what are the underlying structures? What are the mechanisms that lead to a change in behavior? These 3 questions, the 3 why questions here, are an important tool for getting to the heart of a problem that we may want to analyze. And related to the last question that is on this list, is the why do things change, is of course related to our inherent our original motivation for studying systems, and that is we're typically looking into the future, and we're not happy with the status quo. So we would like to change the system, but how do we change a system? So we first need to understand how the system can actually be changed, and in order to to do this systematically, Donella Meadows, one of the 4 thinkers, the deep thinkers in this area, has come up with a kind of a notion which she calls the leverage points for a system. You see here the system, and then the image is that you can apply leverage by moving away from the system further and further and further, and then you sort of use this Archimedean point to leverage the system and change it into a different state. And what she has observed, or the way that she classified this, is that there are obvious fixes that you can change. So, for example, well, if you want to change the system, let's say if you want to reduce reduce hunger, well, the obvious thing to do is change productivity of your plants so that you can produce more food. But of course, that's just sort of a simple change, and it doesn't think through all the changes that are necessary through the system, because if you produce more food, then you also need to actually increase your supply system, your transportation system, and so on and so forth. And then you go up. So you have different leverage points, you have different ways or different points where you can intervene into the system. And the further you go up this lever, if you like, the more impactful the change will be. So while you may change the productivity of your plants, may already deliver the impact, it doesn't change the overall food system, right? And it's may not necessarily what you want. Maybe you just want to increase productivity because you want to have more food. But maybe you fundamentally ask yourself, hey, that food system as it is running now, this global food system, is just not fair, or it isn't robust, or it isn't serving the purposes of what it was built for. So you may want to think deeper, and therefore going up the ladder higher, to change the system at different leverage points. And that goes as far as shifting paradigms to, to reflect that the original purpose of systems or their functions or the way that we conceive about systems may be fundamentally flawed and needs to be changed. So here's an example of this. So when suppose you're a football coach and you're not happy with the performance of your team or with the status quo, what you can do is you can change individual elements in your system, and you do that by exchanging individual players. But you can also, of course, now think broader and ask yourself, am I playing the right game? Maybe my team is good for playing basketball rather than soccer. So that would change the system fundamentally if you changed the type of game that you want to play, whether it's soccer or basketball. And yet these two still have a lot in common. And so you can go even further and not just change the rules or the structure in which this game works, but rather you can ask yourself, what's the fundamental purpose? And for example, you could, not as radical as we do down here, but you could ask, in the context of soccer and basketball, you could change the whole purpose and ask, what is this for? Is this for, is the team winning that scores the most goals or the least goals? Or is the purpose entertainment, or is it actually sports? And when you change the purpose, you may fundamentally change your assumptions and how you set up the system and what the system function and what it should be and what the system actually delivers. So this reflects, or is a sort of a simple example of how you can think of this leverage points in a system, that there are different ways in which you can think about a system and try to change the system because you're not happy with what it currently does. Our football player analogy would be here, where you just sort of change the individual elements on the first stage, you change the system rules, maybe here, and then fundamentally here you can ask that question about equity or equality, where you really ask that point or that question, what is it that not only what is this goal about, but what are the challenges in the future that we want to address fundamentally with our systems? Okay, so in this section we've heard about systems. We've heard that systems do change. Sometimes they change rapidly. Systems can recover when they are resilient. Systems can be changed, and where we put the leverage point for change determines the kind of change that we can make. We will never be able to solve the climate problem by just fiddling around with adjusting a few numbers and increasing the carbon price a little bit more. That may work to some extent, may have a certain effect, but what we of course need to do is we need to fundamentally transform our energy systems, our consumption systems, and so on and so forth. I don't want to go into these details, but you can see that it's not just about changing a number of parameters here and there. Okay, I think what I will do is I will stop here. We've been doing this now for 2 hours. I have a little bit more material, but I think I'll stop here. I also didn't plan so much more time for this activity. But we have a few more minutes for questions.
I like how those structures are like normal distribution graphs. Like you see a shape and that tells you kind of the behaviors of that. That's yeah, really interesting. Thanks.
Thank you.
Thanks, Fabien, for a very informative presentation. Now, a small question or comment. I'm a scientist. I was working on the developing a COVID vaccine at the CSR in South Africa. Remember during COVID, even the supply chain got constrained. And then it was very difficult for us to get chemicals coming from outside. And that delay had the very big, if I can put it, very big consequences because we could not achieve our objective in the lab because of that delay. How do you describe it in terms of the system that was broken?
I'm not sure. This is a rather complex question. How do you describe the system? I think what you're referring to is that that there was a supply system, and it's a supply system for any it's like for any goods or service. That supply system is imperfect in the sense that it also had delays. There were probably intermediary actors that that delayed the process. So the way that you want to think about it is, again, you have an ultimate objective of your system that produces vaccine, and the production process depends on supply chain. Supply chains look or can be made look like trees, like logical trees. They don't necessarily are working like they don't necessarily have feedback loops. But if you look at them closer, you find that there are these feedback loops as well. And I guess a careful analysis would show that that there are parts of the system that are I guess if you think about a network, are more central and are more important, almost are more central to the network, and therefore more important for the system to perform. So in this particular case, you would probably use network analysis to figure out what is your level of redundancy, what's your level of throughput, and so on and so forth. And then you would devise ways in which your supply system or your supply network becomes more resilient by maybe adding new nodes, in particular new suppliers of intermediary products for your vaccine. I don't know whether this is something that you want to hear, but yeah, I think network
thank you.
analysis.
Thank you very much for the element of response. I think it was about, tackling a very big problem, issue, challenge that we have in Africa. And this is a question that I could maybe address to the African Academy of Science, because what we saw during COVID, like we didn't do much as the African to get our own solutions. And then we got the vaccine coming from outside because one of the reasons was because of the delays that we got in the system, in the supply system. Thank you.
Yeah. Thank you. Abdullah?
Hi, Fabian. Thank you very much for the presentation, wonderful presentation. My question is regarding data collection for these models. Like if you are going to, develop, system diagrams or any kind of system dynamic models or agent-based model for the community-based research, what is the best way to collect data for these systems or for this model?
Yeah, I think, obviously this is a very important question, but it's also fairly generic, and it depends really on the context. So as you will, I hope it sort of has come across that when you work with different stakeholders, it's unpredictable what they will say, how they as a group think the system works. Because if it was predictable, then I could do it myself, right? But if you are at the community level, you want to listen very carefully to what the stakeholders have to say, what is important and what isn't. And that determines, of course, very much what kind of data you need to, to figure out when you then want to build a model to make sure that the model produces the results that you need. So let me sort of put this in two boxes. So the first box is, how do you actually design a system diagram and a model that reflects adequately what the stakeholders think are important? And that's already a sort of a process. I said maybe you need half a day in a group to decide this, then people need to think about it once again, then they come back, and so on and so forth. And then there's this point that you're raising, how do you translate then this into a model? So first of all, you have to ask the question, do you actually need a quantitative model, or is it enough to just have a common understanding of the qualitative inputs? Now, from what I said, probably most of you will say, well, we need a model to understand the system better. That's fine. And then you need data. And then it depends again. To my mind, it's really, really important. First of all, context is important. And objective is important, right? Again, if you want to model every single let's say every single street canyon for air quality, right? Then you need a highly resolved model, and you need lots of data, and you need lots of expertise, right? But if you're more interested in what's the overall pollution pollution level over a certain area, then of course you can work at a more aggregate level. So depending on what kind of question you're interested in, you will have a more or less appetite for data and for analysis. So it's very hard to say what kind of data you need and where you find that data. I have a colleague here, when we talk about community level, I have a colleague here at IIASA who very strongly believes in the use of citizen science to generate useful data for all kinds of purposes. And others think more, yeah, well, we need more statistics that are official. Others think more about, it's not just about data, but the data, what is important is that the relations are properly designed and so on and so forth. So again, I guess I'm babbling. It's difficult to say from afar what the exact circumstances are. So context is important, and purpose is important for answering that question.
Okay. Thank you. Thank you very much.
Thanks. Dr. Namu?
Thank you for the presentation. Excellent presentation. I have one question on the representation of the system. And in one of the slides, you indicated we could represent systems where we have systems within the system. So subsystems, you indicated we can represent them as hierarchical, so hierarchies. And my question is it the same as if I presented them as nested circles? So I have smaller circles inside bigger circles to show the subsystems within the bigger system. Thank you.
So my understanding is this is about hierarchies, but I'm not quite sure I really understood the question. So was it whether it is how to represent the subsystems?
Yes.
Yeah, that's kind of yeah, whether these are circles or anything else doesn't matter so much. So I'm still not quite sure. Let me just try to answer in the way that I understood the question, and then you correct me if I got it or not. So in principle, the idea is that a system depends on, a system consists of elements that interact. And in a sense, from a sort of, if you like, in a certain language, these are kind of the atoms of the analysis. They cannot be split any further. These elements are just there. They have certain properties and they interact with each other, but they have no substructure in this particular analysis. And so you can, in a very simplified way, you can think of atoms as being like little billiard balls that don't have any structure themselves. And then, but then as soon as you start to realize that what is important about these billiard balls is their internal structure and how maybe they are not, sorry, maybe these billiard balls are changing over time, so their properties are changing. Then you need to think about what is the subsystem, how do I represent the subsystem, and so on and so forth. In practice, when you draw a systems diagram, then you either you have these billiard balls as part of the elements, and then they don't have any structure, or you say what is in the billiard balls is important, but then you have to bring out everything that is in the billiard ball and forget about the billiard ball. Then the billiard ball itself is just an artificial boundary that you don't really work with because you're interested in the substructure. Did I address that question somehow?
Yes, that's okay, because my question is now, and I understand the explanation, because my thinking was, do I present them as staircases or do I present
I'm sorry.
them as apples?
I'm sorry, staircases or bubbles. Well, I mean, the staircase or the sort of the hierarchy is sort of a mental image. When you are thinking about a system, you know that you put them on two-dimensional paper is just an artifact. You could, or let's put it differently. So if you represent subsystems in the ladder from top to bottom, then clearly the orientation sort of matters in the sense that you want to say one is more of an aggregate than another, right? Whereas a systems diagram, you can, in principle, you can rotate this and you can move around the different bubbles, and it's just a matter of what's the simplest way of rearranging these different elements to make the system, let's say, understandable. And in this context, if you understand that the elements are important, you want to have them all in one picture rather than in a hierarchy. So in that sense, the hierarchy picture or the staircase or the ladder picture is there just to illustrate a particular property of how systems at different levels interact. Whereas the bubble picture is really then taking it seriously and saying, well, fill this notion of interaction, fill this with life, and explain to me how a subsystem really interacts with a supersystem. I hope this is helpful.
Thank you. That's better. Thank you.
Thanks. Okay, Eunice.
Right. Thanks for all the knowledge you're imparting. But I've been wondering, ultimately, what the system gives you, the model produces, is a function of what the elements that you have imputed into the model.
Yeah.
Now, that also means that what you get depends on the knowledgeability of those that are doing, trying to get the model and their ability to identify all the elements that should be in that model.
Right.
So,
yes. Yeah.
who will be in the best position to to lead this kind of effort, because it's apparent that one person cannot just do it. It will be a team. Who will be in the best position to ensure that all the elements that should be in that model are in that model? Thank you.
Yeah, thanks. So again, these are three interesting and interrelated questions. So clearly, again, who can decide what needs to be there? To my mind, when you do this well, then you do this in a group of people, and with the understanding that each of them has a voice, and that none is just sort of dismissing the others and saying, oh, but you know, I have more knowledge than you, and therefore I can tell you what is right or wrong. So you don't want to have an economist in the room, or I'm sorry, I'm bashing economists, but suppose you want to have you don't want to have an economist saying the local knowledge or the local importance of smallholder farming isn't important, and that's why this isn't part of the model. If the community thinks that this is important, if as a group the group comes to a conclusion this is relatively important, then it should be part of the systems model or the systems diagram. So there is no single person who will do this. Having said that, what of course helps in these kind of processes, when you have stakeholder engagement, what we call transdisciplinary research, then it is useful to have a facilitator who can make sure that all voices are heard and can also facilitate the discussion of what of how a reasonably complex system model or systems diagram can be designed without getting lost in all the details, right? So the way that I think about it is you need some kind of guided process, but it's a bottom-up process where somebody is just facilitating that process. And the group decides what the elements of the model are. So what does the model then produce? This goes back to probably earlier questions, and something that I haven't really talked about, and I just didn't have time to talk about it. The model itself, of course, is not a solution. It's not even giving you a solution, but it is allowing you to, in the first place, to simulate a model. It's a tool for thinking, right? We've seen now several complex systems that we have translated into diagrams, and the diagrams already help us to think through this. What would happen if we changed one of the parameters here? What would happen if we changed the birth rate here? What would it mean for the population, and so on and so forth? So a model will help you to think this through in a more easy way. It's not supposed to give you really, I mean, it's giving you answers to certain questions. It's supposed to give you answers to the questions, what if? What if we changed this parameter, what would be the result? What if these two things were connected in a different way? What would happen? The model cannot give you an answer to what should be the case, to the question what should be the case, right? So you cannot ask a model, tell me what is the right level of climate change, or what kind of species should we sacrifice, and which species should we save? This is not what a model can tell you. The model can only tell you, what if you decided that you can only save 10,000 species, and you then assumed that you want to focus on mammals, what would be a good choice under this scenario, right? So it must be really well understood that each model is designed for answering specific questions, and the questions need to be discussed beforehand. So when you're discussing how you want to design your systems diagram, you want to already discuss also what kind of questions do I want to answer with this kind of systems diagram and with this kind of systems analysis or systems model, right? And if you have, when you have the wrong model, you cannot get good answers to the questions that you're having. So this is really important that it's in the way also an iterative process, right? So you may go through the process of designing a systems diagram, a systems analysis, already figuring out what are the important issues. Then you come together as a community, you design your system, you even do a few simulations with your model, with your simple model, and then come to the conclusion, no, this is not the kind of questions that these are not the kind of answers that we were asking for. We need to redesign our model, our framework, our thinking. We need to redesign it to actually come out with the answers to the questions that we really have, right? So the way that I like to think about it is that systems analysis is an iterative process. So this is not sort of so it goes in circles itself. It's also a system, if you like. You start with a question, and then you find out more, and then you go back to redefine your questions, and so on and so forth. That's, to my mind, what systems analysis is also. It's going a little bit in circles. It's iterative. It's learning, and it is a way that the community can learn, or rather several people at the same time. Think about it this way. Sorry, I'm going on a tangent, but think about it this way. When you learn, or when you think about learning, then you often think about you learning as an individual, right? So you learn a new language, so you have to sit down and learn vocabulary and learn the grammar. You are learning, you're making progress. But what systems analysis is doing, or what systems thinking is doing in these models, is to help us learn together as a community, as a group of stakeholders. It's tools. It's like a vocabulary trainer for the individual that learns individually. A model is a tool for a group of people to learn about each other, learn about the world, learn about solutions. And that happens a lot in circles because it's a relatively complex problem. One last thing. So I've talked briefly about systems. We've talked about systems thinking. Now I've used the word systems analysis, which can be, somebody wrote in the chat, the systems dynamics is like where you go through the process of actually sitting down and writing down the diagrams and analyzing the system and trying to figure out how the system interacts. Applied systems analysis goes one step further, and that is applied systems analysis is not just interested in trying to understand the system as such for the sake of understanding the system, but applied systems analysis always has a decision maker in mind, right? And so you design as an applied systems analyst, you already not only think about what is the problem that you're discussing, what is the challenge, food security, water supply, climate change, but you think about who is the decision maker. Is it the global social planner, as many of the climate systems modelers assume that there is some kind of God-like person who can decide what's the right carbon price and who's mitigating how much and so on and so forth? Or is it maybe the local stakeholder community? Is it the local mayor? Or is it a particular parliament? Or is it the family? Or who is taking the decision? And if you understand who is actually taking the decision, you need to put this back into your model because you want to model what happens if a decision maker takes a particular decision, right? And then it's not good enough to assume that there is some kind of omniscient God who takes a decision. That's not what the reality is, right? So good applied systems analysis is good systems analysis plus thinking already about who's the decision maker and what kind of decisions can the decision maker actually take. Okay, this is it's a lot and it's getting late. There's one question from Simon. Now let's see. The change but involving community research with different backgrounds.
I wanted to say something.
Yes, please, Simon.
Not really a question. We are learning for the purpose of doing our proposals well for the Belmont, or seeing how to approach our problem solving in the areas we have chosen to do the study.
Yep.
So the conversation you are giving us, I see two things. One, there's a system change. There is we are basically looking at the something that has happened in the environment. There's a trunk on disaster risk. Disaster risk management or water resource and so on. So there's something happening in the water resource environment, and which we need to address together with the community and everybody else who is affected in ways that we understand what is going on and solving it. So there's that system part of thinking.
Yes.
Then I see you are also having a conversation revolving around who is involved. We have different people, different scientists from different backgrounds. Social scientists are particularly emphasize that they must be included because they are solving community problems.
Right.
And then you are telling us that actually we must gel as a system. The system contributes to solving a problem or to assisting the system to function. So I think that's a conversation here, that we must, in one way or another, operate as a system ourselves to address a system in the environment. I think that's a clarification I thought I needed to mention here.
Yes, thank you. Thanks for putting this into very elegantly into very few words, what I've tried to convey in a very complicated way. Yes, in a sense, you need to, we need to think about how can we organize knowledge and the supply of evidence into a decision-making process so that the system can actually change. And that itself, organizing that knowledge and organizing the processes in which knowledge can enter this decision-making process, that is already a question of systems analysis. How do I create that kind of knowledge or information? Another way of saying it, I'll give you an example. So as I said, we're using a computer model to assist, for example, the European Union, but also decision makers in India, to assist them in designing good policies, right? Now, you can ask that question, what kind of characteristics does such a model have to be useful for a decision maker, right? And then you already you probably you already can guess the answer. The answer is it needs to be scientifically credible, but it needs to be able to translate all the scientific content into a few decision options, right? So we go with our model, we create option A, option B, option C, and say, look, if you choose A, we can simulate what would be the outcome, and then we can do this for the other options as well, and then the decision maker can take a decision based on the information on the particular options that can be taken. That is different from just doing science where you say, oh, I want to find out the vulnerability of a certain income group in a particular country. That's good science, but it isn't good systems analysis because it doesn't give you an option and it doesn't analyze an option. It just assesses a particular a particular characteristic, namely the vulnerability, which can then be used in other research. Good systems analysis, and this is the challenge that you're now facing, is to bring it all together and think about how can we make the knowledge about the system useful for the decision maker.
Thank you very much.
Thanks, Simon. This was excellent summary. Edward.
Yeah, Fabian, thank you. I just need a little clarification here. I am not a system thinking expert at all. I think this probably is my first exposure to this, but of course, I think my interaction with many others kind of like gives me the room to ask some questions. How different is this from multi-criteria decision analysis, for instance?
Multi-criteria analysis is one of the methodologies of systems analysis, if you like.
Okay.
The idea is, yeah, it's just it's sort of a sub-discipline, if you like.
Okay.
Yeah.
Okay. So yeah, I'm asking because of course we do sometimes use multi-criteria decision analysis to help decision makers to make some decisions based on in terms of water resources allocation, on if you kind of want to rejuvenate a system, harvest rainwater, or decide on where you want to put your recharge facilities and things like that. And I see that we kind of pull all these factors together to analyze and see which one is what and how each of those impact the system, and finally kind of make some recommendations. So
yeah,
that's why I'm asking that.
Yeah, no, I think, and thanks for bringing this up. I didn't talk about this. Multi-criteria analysis is, of course, exactly what should come out in the end of a good analysis, that you are aware what are the criteria, what are the different outcomes, what is the space of options, which criteria can be satisfied to what extent.
Yeah.
And then it's a matter of, again, iteratively going through with the decision makers of alternative scenarios and figuring out what are limitations, what are synergies, what are trade-offs between different criteria and objectives here. I think the purpose of this session was, for you, I guess one of the purposes was to lift you out of this operationalizing of what you actually do in a multi-criteria, and to give you a little bit more context on where is this actually coming from. And the criteria, so again, to sort of think about the criteria not as, again, given, these are the criteria against which you have to make this assessment, but rather the criteria and the analysis themselves are the product of a process that comes earlier, namely to decide as a group of what are the kind of questions that we want to answer, what are the criteria that are important, and so on.
Yeah, thank you. Thanks. Yeah, it does work it. Yeah, thank you. Yeah.
Okay, then I would suggest that I hand back to Lebo. From my perspective, this was super exciting. I think you're a great group. You ask super questions, super interesting interactions. I really enjoy that. And whatever you do in your next steps, I wish you good luck and hope that some of you are successful in getting to these projects.
Thank you very much for this wonderful presentation.
Thank you.
Thank you very much, Fabian.
Thanks. Good luck then.
I think everybody enjoyed this session.
Lebo?
We appreciate your input and direction. It gives us more energy now. Sometimes you are groping in the dark. You don't exactly know where you are heading, but I think you have some idea of what is expected of us. Thank you so much.
Great.
Yeah.
Thank you. Good.
Thank you. Thank you very much.
Thank you. Thank you.
Bye.
All right. Thank you so much, Fabian.
You're welcome, Lebo.
everyone else, I know you're gonna ask the question about whether will these presentations be shared, and so they will be shared. We're just creating a link. I'm just gonna hand over to my colleague, Faten. Please just tell everyone about where we're gonna share the recordings and the workshop materials.
Thank you. Thank you very much, Dr. Fabian, for this impressive presentation and also for the great interaction that we had alongside this session. I would like to make maybe two announcements. One is on the material are recording. So now we are in the process of putting everything together, and everything will be shared on one open platform. So you should expect an email come from us soon on the instruction how to upload them, download them and also get the material and also interact with us. The second announcement is to announce that we are still moving with the webinars and the training to support the Belmont Forum Africa Regional Call. So you should also expect another communication from us in the upcoming week on the plan for January 2025. So thank you very much. It was really great having you all, and we look forward to see you very soon again. And we will also follow up with all the needed material and recording soon. Thank you very much. I hand over to my colleague Levo.
Thank you. Thank you so much, everyone. Thank you for coming. We really appreciate your participation. Brings us to the end of the workshop. Thank you all. Thank you once again, Fabian.
Thank you, and thank you from Nairobi.
Thank you, everybody.
Thank you.
Bye,
Bye.
everybody.
Thank
From
you.
you.
Bye-bye.
Bye.
Thanks, everyone, and bye.
Bye.
Bye-bye.